Let's focus exclusively on fields. We've already seen many examples of enlarging a field F by attaching an element to it, either concretely by taking this element from a larger field or abstractly by going modulo an irreducible polynomial over the given field F. Now we will look at more general field extensions. This just means a bigger field E containing a smaller field F. Frequently, the vertical line notation is used. We will also study towers of such extensions like F contained in E contained in K and even larger diagrams with several fields. We have already seen that regarding a larger field as a vector space over a subfield is useful. For example, you saw in the homework that the cardinality of any finite field E is a prime power. This is because E must have finite characteristic, and since E is a domain, the characteristic must be a prime number P. Then the subring in E generated by 1 is a copy of the field Fp. As a vector space over this subfield, E must have finite dimension n. And then each basis vector can have p different coefficients from the base field Fp. Okay, now we make a definition. The degree of a field extension E over F is just the dimension of E as a vector space over F, and we denote it using this square bracket notation. Immediately a question arises. If I have a tower K over E over F, then how is the big degree K over F related to the intermediate degrees K over E and E over F? The answer is not difficult, so see if you can find it. The answer is that the degrees multiply, and the reason is simple. If I start with a basis of E over F consisting of V's and a basis of K over E consisting of W's, then all the pairwise products of V's and W's give a basis of K over F. The proof that this is a basis is straightforward, so you should do it now. It may look like a mess, but you just follow your nose. By the way, the basis may even be infinite, but all sums over here are finite by definition of a vector space. To show spanning, take any u in the big field K. Then use the E basis to write it as a linear combination of W's with coefficients in the middle field E. Now write each coefficient C beta in E as a linear combination of V's over the smallest field F and then open the parentheses. Remember, V's and W's are vectors, but they are also in a ring, so I can multiply any two elements. For linear independence, work backwards. Given a linear relation over the smallest field F, first gather for each beta all terms involving W beta and take W beta as a common factor. Now, by linear independence of W betas over the middle field E, the coefficient of each W beta, which is this sum, is 0. And now use independence of V's over F to conclude that all coefficients must be 0. We will deal essentially only with finite extensions, which means by definition that degree is finite. In that case, multiplicativity of degree gives an equality of positive integers, and this places strong restrictions. Here is an immediate application. You should do this exercise quickly. We already saw that 1 generates a copy of Fp inside E and K. So using this tower, multiplicativity of degree gives me that n divided by d is the degree of K over E. In particular, it is an integer. Later, we will prove a converse. If d divides n, then a given field of cardinality p to the n contains a field of cardinality p to the d. In fact, a unique such subfield. You can try to do this as an exercise. Note that we don't yet know how to construct any finite fields except Fp and fields of a few small cardinalities like 4 and 8. Also note that this exercise tells you that a 4 element field cannot sit inside an 8 element field. Okay, the degree formula is a nice dimension counting device, but it is only linear algebra. It gains teeth when we combine it with field theory. So let's review what we learned about field extensions while attaching elements, especially about algebraic elements and their minimal polynomials.